Hello everyone. In the last session, we looked into solutions of linear equations where we discussed about Gaussian elimination method, Gauss-Jordan method, and conjugate gradient method. Here, we also solved a numerical using the conjugate gradient method and obtained our solution. Now today we're going to move into new chapter, which is elasticity in solids. So what do we know by elasticity? Let's say we have a rod like this where we apply force here and another force here and we stretch it up to here. Then when you release the force, the property of this material to come back to its original shape is known as elasticity. We might have heard about Hooke's law, which states that extension, if this was x, is directly proportional to the force F. Then we can write this in this form: F equals to kx, where k is our constant and is known as spring constant. But we generally put a negative sign in front to indicate that this rod is trying to come back to its original shape. If we consider its original length to be L, then our final length will be equal to, let's say this is initial length Li plus x, where x is the extension due to the applied load. Now there is one term here which is known as strain. Strain is basically the ratio of change in length to its original length. LF minus Li, final length minus initial length divided by initial length. Now this value here is our extension x and this is our initial length. Strain is generally denoted by epsilon. Another term is stress. Stress is defined as applied force divided by area. For example, let's say the rod above has this kind of section and we apply force F here and the area be A. Then our stress, which is generally denoted by sigma, will be equal to force divided by area. And there is another term which is known as elastic modulus. Elastic modulus is defined as ratio of stress by strain, sigma by epsilon. Now elastic modulus defines how strong a material is. For example, your elastic modulus of steel will be greater than elastic modulus of concrete. Let's move into different types of strains. The first type of strain is the normal strain. Let's say this is our x-axis, y-axis and z-axis, and we have an element here which is 3D in nature, like this, and we have applied forces in all three directions. That means we have applied force in x direction, force in the y direction, which is Fy, and we have applied force in the z direction, which is Fz. Now this will cause your element, let's say this is the original dimension of the element. Because of the applied forces, what will happen is that this element is going to stretch in the x direction, in the y direction, and in the z direction. If this is the initial shape or dimension of the element, then it will increase in size. It will be like, let this be dy, this be dz, and this be dx, and this is our new dimension. Let's say our x direction increased by a small amount del x. Here also our new length will be dz plus small del z, and new length here will be dy plus small dy. As you can see here, that this one will be bigger in shape than the original one, which means that there will be strains occurring in all the three directions. Now the strain occurring in the direction of the force applied are known as normal strains. So our normal strain in the x direction will be equal to Ex, which is this direction here, will be given by final length minus initial length divided by initial length. So what you get here will be dx minus small del x divided by dx, which will be equal to the small del x by dx. So this is our normal strain in the x direction. Similarly, where this is the change in length and this is the original length. Now we will look into another type of strain, which is the shear strain. Let's say in the same element here, the 3D element, which is this one, we apply a force right here at the top in this area. Then what will happen is that if the base of this element is fixed, then this element will move something like this. It will deform in this way. This is the x direction, this is the y direction, and this is the z direction. In this deformation, due to applied force, let's say P, it deforms by an amount x in the x direction when the original height of this element is dy, and this is our angle theta, which is very small. Then our shear strain will be defined as tan theta, which is given by x by dy, or you can say this is small del x by dy, assuming that theta is very small. Now let's have a look at stresses. First we look into normal stress. The normal stress is denoted by sigma. Let's say in the x direction, sigma x is defined as force applied in the x direction, which is Fx, this one here, divided by its area of application, which is this area here, which is this one. Therefore, we can write sigma x equals to Fx divided by this area would be dz times dy. Similarly, and now let's look at shear stresses. Shear stresses are generally denoted by tau. So for this case here, you can see that the load P is acting on this surface here, dx and dz. Therefore, this stress can be named as tau xg, which will be equal to our applied force P divided by the area, which is dx dz, which is this area here, top area. Similarly, so these are our normal stresses and shear stresses. These stresses are normally obtained through experiments in the lab. Let's say you have a steel specimen which is shaped like this, where we have clamps at these two ends where we apply our forces F. Let's say this is direction Y. Then if the cross section of this element around here, let's say this is XX, is A, then our stress will be equal to Fy divided by area. And if this bar stretches like this under the applied load Fy by an amount delta y, and let's say this is our initial length L, then our strain in the y direction will be given by delta y by L. So in this way, in the lab, we can test any specimen and obtain our stress and strain. Now the stresses and strains obtained by assuming constant cross-sectional area throughout the test are known as engineering stresses, denoted by sigma E. Similarly, the strain will be known as engineering strains, denoted by epsilon E. In reality, what happens is that when this element is stretched, then it will reduce its cross-sectional area, similar like a rubber band. When you pull a rubber band, you can observe that this section here reduces in area. Let's say the new area here is denoted by AT. Then the stresses obtained by dividing force by AT, which is the instantaneous area. That means you keep measuring the area every time throughout your test and then divide your force by that area here. Then such types of stresses are known as true stresses. Similarly, the strains that you obtain like this will be known as true strains. Now, when you plot a curve, stress strain curve, let's plot our engineering stress strain curve. It will look something like this. for our steel. This will be our engineering stress strain curve. Now when you plot our true stress strain curve, then in the beginning, in this region here, it will overlap, and then it will go something like this. This is our true stress strain curve. This region here, as you see, is linear, is known as elastic region, whereas this region here is known as plastic region. There will be characteristic points here, like this one known as proportional limit, this one here is known as elastic limit, and this one here is known as breaking point or ultimate limit. The region Y, the stress strain curve, lies above the engineering curve is because of the reduced area, as we know that our true area would be less than the constant area we assume for the engineering stress strain curve. Now for designing, we'll generally find engineering stress strain curve because this is easier to obtain than the true stress strain curve. If you are doing some kind of modeling like finite element modeling in Abacus or ANSYS, you will probably use true stress strain curve. The relation between true stress and engineering stress is something like this. Your true stress will be given by engineering stress times 1 plus engineering strain, and your true strain will be given by natural log of 1 plus engineering strain. Therefore, true strain is sometimes known as natural strain. Now, we'll look into the relationship between stresses and strains. As you all know about Hooke's law, which states that our stress is proportional to strain. Let's say this is in x direction and this is also in x direction, then we can write this as where this term here is a constant known as elastic modulus. However, this applies only to 1D elements like the rod we discussed earlier in x direction. For a 3D element such as this one, let's say this is x, y axis and z axis, then you'll have normal stresses occurring on this face, and this face here. This will also be sigma x, sigma y and sigma z. Now these are all normal stresses, and also you'll have stresses acting on this surface, which will be denoted by tau xz, and on this surface denoted by tau yz on this surface here, which will be denoted by tau xy. So you can see here that there are 6 stress components. Similarly, there will be 6 strain components. Now, we have to know the relation between these stress and strain components, and we write this relation in this form, equals to a matrix here times, now this matrix here is known as stress strain constitutive matrix. Let's denote this by matrix D, and it will have several values here, and this is a 6 by 6 matrix, so it will be a symmetric matrix. So you can see here that there are 21 unknowns. I'm saying this as unknowns because you have to obtain these values experimentally and are dependent upon material properties. So these values will be different for different materials. For steel it will be different, for wood it will be different, and so on. This is also known as generalized Hooke's law. We can write this in this form: sigma vector stress vector equals to D matrix strain vector. Now the materials in which all of these unknowns are to be obtained, which means that their material properties are different in different directions, are known as anisotropic materials. And there are some elements which show symmetry with respect to the planes in the body, which means that your D matrix will look something like this. And such materials which show such kind of symmetry are known as orthotropic materials. Here, the number of unknowns is reduced to 9. So these 9 unknowns have to be determined experimentally. Before moving further, I would like to introduce to a term called Poisson's ratio, which is very important. As discussed earlier, that when you pull a rod, it will decrease its cross section like this. Now the relation which defines by how much this dimension reduces when we increase the length of the element in another dimension is given by Poisson's ratio, mu. In naturally occurring substances or materials, our Poisson's ratio varies from 0 to 0.5, where concrete will be 0.2, steel will be around 0.3, and rubber will be around 0.5. And some of the elements have negative Poisson's ratio, which means that when you pull, it will increase in other direction rather than decreasing. These materials are artificial or engineered. If we are looking into strains, let's go back into our 3D element. Now, as you know, that increasing length will cause strain in this direction, which will be Ex, here epsilon y. Now due to this strain here, it will cause some changes in this dimension and in this dimension, which will be given by Poisson's ratio. For example, if you are looking at total strain in the x direction, it will be equal to your stress in the x direction divided by Young's modulus in the x direction minus of Poisson's ratio in xy direction minus Poisson's ratio into zx, like this. What it's saying is that the total strain in the x direction will be given by our stress divided by Young's modulus in the x direction, and the stresses produced in y direction will have negative impact because it acts in the opposite direction. Now we'll have in the isotropic materials your Ex will be equals to Ey will be equals to Ez will be equals to E, a constant in all the directions, which means that the isotropic materials will have similar material properties in all directions. Similarly, your mu will be constant in all directions. Again, if you want to look at your shear strains, which will be this one, xy, this is given by shear stress divided by your shear modulus. Again, and in the isotropic materials, this is also constant, so this will be z, z and z. Again, there is a relation between shear modulus and elastic modulus given by, now I'm not going to derive this. If you want to look in a video, you can go to EduPoint and see the derivation. The link to the video is given in the description below. It is generally easier to write these in matrix form. So what you get here will be, now to find a relation between sigma vector equals to D matrix, E matrix, we have to move this matrix this side. So you have to find the inverse of this matrix. So therefore, when you do that, what you will get will be, now this is our required stress strain relationship. This is how you derive your relationship, and your D matrix and this one, all of this will be your D matrix. When you open your first row, it will be like, and you can write this in this form. And what you do here is you open this, you can write your Ex, and then you will have minus mu Ex plus mu Ey plus mu Ez, and you can add one more here, mu Ex, and subtract mu Ex. We have added this term here, which is essentially 0. Now what will happen is that, like this. Now this term here is summation of your strain in all three directions. Now this is known as EV, which is the volumetric strain, which gives us how much change in volume has occurred in the element. Now this is reduced to cancel out this one here, and then you can write, sorry, this will be plus, and you can multiply by 2 and 2 here, because our shear modulus equals to E by 2 1 plus mu, as shown here. Therefore what you can write here is, this here and this here are known as Lamb's constant, where lambda will be equal to z will be equal to, so these are the Lamb constants. If you want to write this expression here using Lamb's constant, so these are the relations using Lamb's constants, which is generally easier to express. If you look at our volumetric strain, which is EV, that equals to EX plus EY plus EZ. Let's see what EX plus EY plus EZ looks like. You can combine this and you will get 1 minus 2 mu by E into, so this is our volumetric strain. So our volumetric strain equals to EV equal to 1 minus 2 mu by E sigma x plus sigma y plus sigma z. Now let's move into another section, two-dimensional problems, in which we'll discuss about plane stress and plane strain elements. Let's take a thin plate like this. Here we take a case where the height, the thickness is very small compared to its other two dimensions. In the plane stress problems, your stress in the z direction is taken as 0, which means that your shear stress in z direction are 0. In cases where we apply in-plane loads like here Fz, Fz and Fx. In cases where we have applied load like this in the xz plane, your force can be here, here, here and here. So this is our xz plane. In these cases, the stress in the vertical direction is taken as 0 in the plane stress problems, which are the thin plates like thin slabs. Now if you substitute these values in our constitutive relation, which is this one here, we will obtain, so this will be our D matrix. Now if we expand the third row, which is the sigma z equals to 0, and formulate the equation, we can write, which is interesting because what happens is that in a 2D element, say let's say the thickness is very small, when you apply forces in this direction and this direction, it will stretch. However, if you look at the cross section, it may decrease. If this is our original thickness and this is final thickness, our final thickness will be smaller than our initial thickness. Therefore, it will cause strains in the G direction. If you look at our other equation, which is this one here, and here we can put sigma z equals to 0, this one 0, this one 0, and open. Now if we want to find our stresses, we have to find inverse of this matrix here. So our stress vector so this will be our stress strain relationship for 2D plane stress problem. In the plane strain elements, what happens is that generally you will have a section which is very long. Let's say a dam like this, which is very long, or you can have a pipe which is very long. Then because of these materials, the strain occurring in this direction, which is the G strain, if this is X, Y and Z, because of longer length, the strain occurring in the Z direction is assumed to be 0. So in this case, our strains EZ, gamma XZ and gamma YZ are assumed to be 0. So in this case, if you have this equation and you can substitute your EZ, gamma YZ and gamma ZX equals to 0, so what we'll obtain here will be sigma Z. There will be stresses along the Z direction but no strains, will be equal to mu sigma X plus sigma Y. You can try this. It is similar process to this one, but here you have to substitute your EZ equals to 0 and expand your EZ and you can get your sigma Z. And then we can look into this equation here and we can find our sigma X, sigma Y, tau XY should be equal to, what we did here is we just reduced this matrix here, taking into sigma X, sigma Y and then tau XY, as we assume this one 0, this one 0 and this one 0, and we have written this matrix. So this is our stress strain relationship for plane strain elements. You can look into my other video in the other playlist where I have modeled 2D plates and I have done some numericals using this plane stress and plane strain problems. You can go there and see how these matrices or these relationships are used to obtain the stresses and strains in 2D elements. Sometimes you'll also come across some elements which are symmetric about certain axes. Such elements are known as axisymmetric elements. For example, we can have a cylinder like this which is symmetric about this axis. We can have this section like this which is also symmetric about this axis. So in this case, when you take this section out, you will see pressure generated here like this, and we can represent such problems in polar form as well. If this is theta, let's say this direction is R and the vertical is Z. In this case, we consider gamma R theta, gamma Z theta equals to tau R theta equals to tau Z theta equals to 0. Shear strain and shear stresses with respect to theta plane are 0. Then what we'll obtain is your stress strain relationship as where your ER will be equal to change in length in the r direction by initial length in the r direction, and Ez will be equal to change in length in the z direction by initial length in the z direction. E theta will be, and gamma or z will be equal to, so here what we're considering is change in length in this direction is taken as u and this direction is taken as w. So this is our relation for axisymmetric elements. Now for engineering books, you can contact Engineering Books Nepal in Facebook, which is now working together with Kitab Kiro, which is an online book delivering company. So you can send a message to Engineering Books Nepal. They will act as a correspondent with Kitab Kiro, and hopefully you'll get your books delivered from Makala Publication House or any other engineering books that you want to refer. So today we looked into elasticity in solids, where we discussed about stress-strain relationships, 2D problems such as plane strain problems and plane stress problems. We'll use these equations in chapter 4, where we will do some numerical examples on 2D plate elements. This is it for today. If you have any comments or questions about this video, you can comment below or send an email to zitinabacus@gmail.com, which is in the description below. See you next time. Take care. Thank you.